Welcome to Project Genesis's Introduction to Solid Propellants. I'm glad y'all could make it to the meeting today. They're presenting this presentation for SciTech 2021. And we're doing a recording of this presentation so we can post it up to our page later on. So, an introduction to solid propellants. So, the premise of this group essentially is going to be researching solid propellants and the pourability of solid propellants. In order for you guys to understand what's going on with that, we got to introduce the topic to you first. So, what is a solid propellant? We've also got a disclaimer on this that is just the disclaimer is we're not responsible for what you do with this information, and viewing this presentation constitutes agreement to that disclaimer. We're also not responsible for any of the dangers or potentially dangerous things that happen if you attempt to do this yourself. So what is a solid versus a liquid? That's the very basics of it. So solid motors are the oxidizer, or is an oxidizer plus fuel plus a couple of binding chemicals. And then one of the advantages of that is they tend to do a good job of lifting very heavy things like the space shuttle, the orbiter and all that up into space, but they can't be turned off once they're started. So the solid motors we have, we're practicing using them just because they're a little bit easier to design and work with than liquid motors, but that comes with the downside of not being able to shut them off once they get started. Whereas liquid engines, they just need oxidizer and fuel, and they can regulate the amount of thrust they're putting out through the nozzle. But oftentimes complex turbo machinery is needed because pressure-fed rockets aren't quite enough. And there's a few different cycles of liquid engines. There's open cycle, closed cycle, and then full flow cycles. You can see the little images down here, and that just dictates how the engine runs. So most liquid engines run using turbo machinery, and that turbo machinery is powered off of a liquid fuel mix, often fuel rich, to get the turbo pump moving fast enough to pump fuel out to the chamber. Next thing, so chemical composition of a solid propellant. So to create the propellants we've created, we're using ProPep, prior club knowledge, and knowledge from other universities. So kind of how we went about doing what we're doing is we had a couple of recipes that were packable recipes and a couple of recipes that are pourable recipes, more on that later. And we kind of compared the differences in the ratios and the ingredients in those things to determine these are the things we think are like the major differences or what affects one propellant being pourable or one propellant being packable. And we use ProPep to just give us rough numbers for what the ISB is and other things like that of the motor so that we can start burn sim or model it with other programs. So chemical composition in SRB. So our propellant is slightly different, but the typical composition for the actual composition for the SRBs was PBAN as a binder, fuel as an aluminum powder, oxidizer was ammonium perchlorate, the curative, they had an epoxy curative, and then they used iron oxide as their additive. And this was an APCP propellant and ammonium perchlorate composite propellant. Our propellant is a little different. We use a few more things. So we use a different binder. We use HBB. We use aluminum powder as our fuel, and we use ammonium perchlorate as our oxidizer. And then we have MDI as our curative, IDP is our plasticizer, and then we use a few additives in our propellant, one of those being oxamide. And the oxamide is a burn rate suppressant. So we're trying to keep our motor from burning as fast.
You can see in the bottom right there, there's some ammonium perchlorate being poured into a cup. This is how we measure during mix sessions, but it's interesting to see the chemicals. We also have the chemicals up there on the table in that upper photo.
So solid propellant types, what I was talking about before. So there's two different types of solid propellant. There's packable propellants and there's pourable propellants. The main difference is how they're cast into their grains and what they can be used for. So packable propellants normally contain a higher solids percentage and normally have a higher ISP because they have that higher solids percentage in there. Additionally, they need to be packed into casting tubes. So for a packable propellant, you can't just pour it into the grain. You have to kind of roll it up into little snakes like you see in that photo, and then you have to drop them into the liner, and then you have to pack them down with a tamping rod in order to get them to seat nicely and get all the air bubbles out of there. And they also, speaking of air bubbles, they tend to form more air pockets in that propellant because you're tamping that propellant down. It doesn't naturally want to settle down into place. and they can't be used for larger motors due to that packing requirement. So when you're creating a larger motor, it's harder. One, it's harder to pack because there's more propellant and a lot more you have to push around with the packing rod. And two, those air bubbles are less likely to come out to the top. And those air bubbles are really bad in a propellant because those air bubbles can lead to detonation of the propellant. Or if we're burning a motor and there's big air bubbles in it, those air pockets can explode and destroy the motor. And that would be very bad during a test. The other type of propellant is a pourable propellant. These normally contain a lower solids percentage than packable propellants, and therefore have a lower ISP than a packable propellant. Additionally, they're nice because they pour into the casting tube. So as you can see in that photo, you can use a funnel to pour them or cast them into a casting tube, so that you don't have to pack them in and they settle out nicely. And they tend to be roughly the thickness of like a thick pancake batter, honey, maybe a very thick syrup, is kind of where you want to be, because if you go very thin on it, then you lose a lot of ISP because you're going to be very low on solids and some other ingredients. And but if you go as viscous as possible while still remaining pourable, then you can get a pretty high ISP that's somewhat comparable to the Packable. It's still slightly under, but close. And then these can be used in large motors, and this is what the SRBs used. Is they use a pourable propellant, because when mixing a very large motor, you really want to avoid those air pockets, and the propellant settling out on its own is very useful. So next thing for us is mixing propellants. So this is something I would not advise you guys do at home. It's very dangerous. There's lots of room for mistakes. We've got it down to, or we've done a fair amount of mix sessions, and we have procedures for how to do these and steps to mitigate risks that happen during the mix sessions, but they still can be dangerous potentially. So mixing propellant requires careful preparation and execution. So what that means essentially is we've got several like 10 to 20 page documents that outline how we're supposed to mix propellants, what are the risks that occur when mixing propellants, what are the mitigation steps taken, things like that. So you got to be very careful when mixing propellant. And then additionally, in our mix sessions, we have a little ranking system to try and keep the more experienced members in charge, or keep the more experienced members in charge during a mix session. That way nothing goes wrong, because they know what's going to happen next, or what this is a step that should occur next. This is the risks involved. This is this and that. So the mix master ranks we have is a mix master, mix certified, mix observer, and then one more we didn't list because it's a little less important, is a senior mix master. These kind of just outline, can you schedule a mix? Can you handle chemicals during the mix? Can you measure chemicals? Can you just hang out during a mix? So these kind of show what people can do during a mix, depending on their experience, or if they've taken this certain test or this certain test, to make sure that they have knowledge, or enough knowledge to handle that position. And then the next thing, or during mix sessions, we add chemicals into the mixing bowl, about maybe every half hour or so, depending upon the step that we're adding chemicals to. And we use industrial grade mixtures for it. So another important thing to note when mixing propellant is you want to have a mixer that can be on for long mix times, because the mixer can be on for up to an hour, possibly even, when mixing propellant. So you want a mixer that's not going to overheat or anything like that, or burn out when you're mixing propellant, because that would be very bad. Additionally, you want to be careful about what spade or like attachments you choose when mixing, because for us, we have to choose an attachment that does mix propellant but doesn't put too much friction into the propellant when it's mixing. So that's another thing you have to be careful of when mixing propellant with an electric mixer, because a propellant is also hand mixed actually. The next thing we use are vacuum pumps and shaker tables to extract air bubbles from the propellant. So that's another big thing, is again removing those air bubbles from the propellant, something you don't want in there. So these mixers tend to incorporate a lot of air in the propellant, and we want to get that out of the propellant before we cast it and create a bunch of air pockets in our propellant. And the propellant is then cast into casting tubes to make grains of propellant. And that's the very final step. Once all the propellant's mixed and all the ingredients are added, we've got little liners. You can't see them in this photo, but we'll show them to you later. Those liners are what we cast the propellant into to actually make up a motor, because the motors we use are kind of, they are cartridge loaded in a sense. So that's what we have, or that's what we cast into before we set the motor up. And we'll go over that a little more later in the motor section. There's a few different types of grains also that you can use when creating propellants. So the type of grain and motor we're using is a segmented tube grain, and it's just going to be a grain with a hole in the center. So the advantage of this one is it gives you a relatively neutral burn rate, which we'll hop into the next slide about. But each of these grain geometries on the inside affects how much surface area the motor sees. And that surface area directly determines how the motor burns in, the chamber pressure, and the thrust of that motor. So different types of liners, or not liners, sorry, casting, what's the word? Core mandrel. That's the word for it. So different types of core mandrels can be used to get different shapes inside the case to change the amount of burning area you have inside the case at any given moment in time. And onto that, the types of burn we have are progressive, neutral, and regressive burns, and then a few other ones over here. So the thrust and chamber pressure that a rocket motor generates is proportional to the burning area of the motor. So depending upon how much surface area is present at any given time, that'll determine how much thrust or chamber pressure the motor has at any given point in time. So for instance, in a grain like this kind of marks how the grain burns over time, and the surface area in this grain remains relatively constant, and you get a relatively neutral burn until the very end, where you just got a little bit of slivers of propellant at the end there burning. So as you can see in the tubular, the rod and tube, and the other grains like that, you can get different types of burns depending upon what layers are burning at any time, or how much surface area in that motor is burning at any given point in time. So progressive burns are nice if you want a rocket that slowly accelerates and has a max acceleration at the very end of the burn. Neutral are nice for just a steady acceleration throughout the flight. And then a regressive burn will give you a really big kick off the launch pad and then start slowing down in acceleration as the flight passes. And then you got a few other very interesting designs. Is a dual composition would be two propellants in a single grain at once. That would be the line dividing things here. And then a dual thrust grain is another very interesting one that throws out most of its thrust at the very start of the motor and then starts to burn slowly at the very end. So there's a few different types of grains or types of burns you can do inside a motor, or grain geometries you can have inside a motor that will determine certain things about the motor, like the flight characteristics, the acceleration that it's experiencing, things like that. Next, the motor casings. So how we classify our motor casings, again, just diving into all the top level stuff right now, or the basic intro to solids, would be we classify them by diameter when we're doing our thing. So we've got 38 mil, 54 mil, 76 mil, 98 mil, and 152 millimeter motors. So these motors are the various sizes you can have. We are going to be using later on in our testing 98 millimeter motors, because we're designing a propellant, a pourable propellant that's meant for large motors. And that's determined by some of the things inside the recipe. And also because we're doing a pourable, the pourable is meant for large motors, no reason to test it in smaller things. And then what we use for instrumentation when we're doing our tests is pressure transducers to measure the chamber pressure, and then force sensors to measure thrust. And then we mount those both on the aft closure, which is that little yellow gold looking thing at the back of the motor. And then the final thing we do with our motors is we do burn sims. We use those to predict how the motor will burn, depending on how it's built in the surface area inside the motor. So if we choose a specific grain geometry, how will that affect the motor? If we choose a specific spacing on O-rings, how will that affect the motor? So it just does some basic calculations for us on what the burning area inside the motor is going to be and how that affects things. And for instance, a very important one is the port to throat area. That affects, there's a diagram for burn sim later on that I was looking for there. The port to throat area, for instance, dictates the erosive burning characteristics of your motor. So if you don't have the right port to throat ratio, then you have erosive burning in your motor, and you'll start knocking off chunks of propellant off the lower grains in your motor as the motor is burning, which is very bad because those could clog the nozzle. So the parts of the motor, this is the motor without the case. So you've got your bulkheads, your snap rings at the top and the bottom holding everything together. You've got a nozzle that is normally sealed by O-rings that I forgot to put into the diagram here. And then you've got in our 54 millimeter motors that we were planning on testing, not anymore, would be 4 grains spaced by O-rings. So that gives a O-ring space, or that gives burning surface area all the way along the inside tube here. And then it also gives surface area in between those O-rings. So that gives us a relatively neutral burn on our motor. And this is a motor, this is a 98 millimeter motor. This is the data from it, the thrust curve on the bottom and the chamber pressure curve up top. So this was one of the motors that was spaced and gapped similarly to this with, I think, 3 or 4 O-rings in between, about 3 or 4 grains. And then the different size cases, another important thing to note is they have different setups on the inside. So a larger case, like maybe the 6-inch we're testing later on this semester, for that we have to just cast the motor inside into the actual motor case instead of casting it into a liner and then loading it like a cartridge. And that will affect the amount of O-rings we can stuff in between things. It'll affect how the burn progresses during the motor, things like that. So this is the diagram I was looking for burn sim. So this helps us kind of model what's going on during the actual motor flight. So when we space out our motor with O-rings in between, like this, we get a relatively neutral burn as the motor burns through all its propellant, which is kind of what's desired because that allows you to get design for a maximum pressure that's kind of lower than what you might get as opposed to a motor with no O-rings, for instance. Because in this one, you get a maximum pressure of 800, I believe, PSI. In this one, you only get a max of a little under 500 PSI in the motor. And that allows you to get a little case that's a little thinner, a little lighter for flying a rocket. Whereas this one, you'd have to overbuild the case. You'd have to make sure the snap rings can uphold that. So aiming for a motor that has a neutral burn also has its benefits in you can design for more standard pressure inside the motor, chamber pressure inside the motor. Whereas a regressive or a progressive, I believe, burn would cause it so you'd have to design for a higher pressure. So on campus so far, we've tested 98 millimeter motors. We haven't tested anything that massive yet, and this is a test from last year.
Testing in 10, 9, 8, 7, 6, 5, 4, 3.
That was the igniter. So that's the motor fully assembled, along with chamber pressure and force sensor on the back there. That's the igniter. And that's all the propellant burned. And this is a curve of the thrust and chamber pressure. It's not quite in sync because I didn't do a great job of this, but that's roughly how it went for an actual motor test. So, and then the next big thing we're going to be testing on campus is not a part of our project, it's an ESFT project, is going to be a 6-inch motor case. It's roughly 5.5 feet long, something like that. So that's something else up in the motor slide is the case length tends to increase with the case diameter. And then to dive into what we're doing in specific is we're researching the pourability of solid rocket propellant depending on the variation of solids to liquids ratio and binder to plasticizer ratio of the propellants. So this is something we saw when we were looking at the different propellant recipes we'd collected from some various sources and some of the various recipes we've had on campus previously. We looked at the different ratios of ingredients inside that recipe. How are the solids to liquids content? What's the binder to plasticizer content between different things? And some other different ratios we saw inside there between maybe curative and binder, things like that, to see what are the differences that you see in a pourable propellant versus a packable propellant. And the solids to liquids and the binder to plasticizer were the two big things that stuck out at us as being those variables that change. So what we plan on doing is creating our Aether recipe, and we're trying to optimize it to have the most amount of solids possible and the most amount of binder possible, because those increase the ISP of the motor. So we're aiming to get as much of that in the motor while still keeping the motor pourable. And that's what we're experimenting with right now, is changing that solids to liquids content and changing that binder to plasticizer content in the propellant, mixing it and seeing, does it pour into the grains, does it cast into the grains, Is it going to pack into the grains, things like that. So how do the changes in that affect how the motor or the mixing process work, and how that affects the pourability of the propellant coming out of there? Then one other important note is we chose not to do bimodal or trimodal ammonium perchlorate. And essentially what that means is using different micron size ammonium perchlorate to change how things are working in the motor. So using a smaller micron ammonium perchlorate would increase the burn rate, but it would also increase the pourability because you're using lower size particles and they slip past each other better. But we're designing for a ammonium perchlorate that's a bit larger than that. It's about a medium, I think 200 micron is what we have. And that's what we're designing for, just because it's easy and it's the typical stuff you can find. Then how we got to where we are currently. So as I was saying before, we used a lot of associative data from other rocket propellants to figure out what the differences were in packable versus pourable propellants. Again, I was just comparing the ratios that were in different propellants and things like that, looking at what was different, what things changed, things like that, and picking out what we thought affected things most. And then the URI we're doing currently is to just confirm our theories on what makes a propellant pourable, or what ratios we think makes a propellant pourable. And that's what we're researching right now, is doing mix sessions and changing those ratios and just seeing what works. And then we've also done research into the various chemicals and ingredients we saw in those recipes. So we looked into what type of binder we're using, what type of ammonium perchlorate we're using, what are some of the additives they use in the propellant, and how did that affect what was going on inside the propellant, things like that. So looking at the different things in a propellant and how they would affect things when they were all added together, or what one thing might do. Like for instance, the oxamide was added to just decrease our burn rate in the motor, to keep our chamber pressure lower and to keep the burn rate again in the motor lower. That does decrease thrust initially, but just thrust runs over time. So burning slower doesn't necessarily affect the overall output. And that's one of the ingredients we chose to use, just because that's something we're looking for in propellants that the club's trying to produce. Not in specific, but when we're building larger rockets, it's better to launch them steadily than launch them really fast off the pad and then just barely coasting at the end. So that's why we want, again, that slow burn rate. And then what we also have completed is 4 mix sessions. We'll be doing a 5th soon. So during mix session 1, kind of how the convention of the propellant is named is 3 is the recipe number. So that's if any big changes were made in certain things in the propellant. And then B1 right here, 1, 2, 3, and 4 dictate what mix session it was. And then these just dictate the recipe number at that mix session. So the first mix session, we didn't have a pourable recipe. And it had curing issues. So we chose the ratios, those didn't work out. And we also ran into some issues with our mix procedures on losing chemical ingredients to the cups we were measuring things in, because they didn't want to pour out and things like that. So it's a big lesson for us on what was wrong with our procedures and how we could change them and adapt them to be better. Aether 3.2.1 was a not pourable and tested a different binder type, because we were concerned after that first test, because it wasn't pourable. What if the type of binder we're using, because we use binder with additives in it, how does that affect the pourability of a propellant? So we had some binder with no additives in it as a part of another project. We used that, measured that out into cups and replaced it with the same ratios inside that propellant, and took a look at how that affected it. And it turns out that the binder with no additives in it seemed to decrease the pourability by a lot. And we're not sure what exactly caused that, but it seems like the binder with additives is better for our scenario. And then we had 3.3.1, another propellant that was testing out the bounds of things that was not pourable. And then we had 3.3.2, that was our campus's first pourable propellant. And that propellant, we've got a video up on the YouTube channel that we'll show you a link to later. It's the Tom DeVries YouTube channel. That one was actually our first pourable propellants, and what you saw photos of earlier on in the pourable propellants section. And then we also did recently, I think last weekend, was Aether Mark 3.4.1 and 3.4.2. And that one just took where we were with our pourable propellant, increased the numbers a little bit, added some more solids, added some more binder maybe, and just see how close can we get to a higher solids content, more binder content, before things aren't going to work anymore. And both these propellants weren't pourable, so we may have overshot a little bit. And then we use this also to test out our viscosity test stand, which is helping us get relative numbers for propellant on how pourable something is compared to another. So that's roughly what we're doing with our URI. If you want to learn more or like find anything else, the Rocket Development Lab on Twitter and on Instagram will be posting photos and things like that of our project and other projects pretty regularly. And if you want to follow our project in specific, what we're doing, what we're mixing and how that's going, and maybe testing is going to be happening next semester and how that's going, just follow the YouTube channel, which you're probably viewing this video on currently. That's where we'll post more regular updates on during mix sessions and things like that, and testing and anything else we're doing like that. So, any questions from any of y'all? As this is Zoom, I don't expect many people to speak up. Okay, cool. Well, thank you all for coming to the presentation today. I hope you learned something. And I hope you keep track or follow what we're doing, and possibly help us out later in the future. Maybe join Riddle and learn a little bit more about solid propellant. Okay, thank you very much and have a nice day.